Okay, so I want to remind you again that today we will end at 12:10, okay? And there won't be a second lecture today. Not 12:10, 1:10. We'll end at 1:10, all right? And I'll make it up later, so the last lecture, I think, will be May 1st, Monday, May 1st. Now, last time I talked about localization. It's a concept from algebra, okay? And so today we're going to apply localization to equivariant cohomology, okay? So let's first look at free circle actions. Okay. So circle actions are simpler than other types of group actions. And so we're going to be doing everything for circle actions for a while, and then we'll try to generalize it to a compact Lie group. Okay? Now, for a circle action, now I'm going to state a fact about compact Lie group actions. Okay? And this is proven in Lie's book on smooth manifolds. Okay? So it says that if a compact Lie group acts freely on a manifold, then the quotient is a manifold. So let's call the group G. Then M over G is a manifold. And the projection map is the principal G bundle. Okay? So if the action is not free, then it may not be true. The quotient may have singularities. And if it's not compact, you may not get a principal bundle. Okay? But if it's a compact Lie group acting freely on a manifold, then the quotient is a manifold. And you have a principal bundle. And so last time we looked at Cartan's mixing diagram. And it tells us that the homotopy quotient and the usual quotient are weakly homotopic. So there is this map that is a weak homotopy equivalence. So tell me again, what's a weak homotopy equivalence? Yeah, it induces an isomorphism in all homotopy groups, pi k. Okay? And if these are CW complexes, then the weak homotopy equivalence is actually a homotopy equivalence. Okay? And then there's a theorem in algebraic topology that says that a weak homotopy equivalence induces an isomorphism in cohomology. Okay? So hence, there is an isomorphism in the cohomology of the homotopy quotient and the cohomology of the manifold M over G. Now, since M over G is a manifold, it's finite dimensional, and that means the cohomology is 0 above its dimension. So the cohomology of Mg is 0 in degrees greater than the dimension of M over G. Okay? Since M over G is a manifold, and a manifold is finite dimensional. Okay, okay. And now let's assume that, let's just continue with a compact Lie group, G, and so there is a map from M into a point. There's always this map. And this map will induces a map in equivariant cohomology. Okay, and the equivariant cohomology of a point is the cohomology of BG. And so if G is the circle, then the cohomology of the classifying space is the cohomology of CP infinity, and that is with real coefficients. That's the polynomial algebra R of U. Okay, and so let's see. Okay. Now, so this means that the equivariant cohomology with S1 as the group is an R of U module. Okay, you can multiply by polynomials in U. Okay, and now, so if you take K to be large, let's say K is greater than the dimension of M over G, then U to the K times equivariant cohomology this will have degree at least K, which is greater than the cohomology of the manifold M over G. So this will be 0, since its degree is greater than K. Yeah, its degree is, it's 2K. Since its degree is 2K plus star, right? Because U has degree 2. And so this is going to be greater than it's greater than or equal to 2K. K is, let's say K is at least 1. Then this will be greater than or equal to K. And that's greater than the dimension of the manifold by hypothesis. Yeah, so you're above the dimension of the manifold, so the cohomology will vanish. Okay? And so this says that equivariant cohomology with circle coefficients when the action is free is U torsion. So theorem, if S1 acts freely on M, then the equivariant homology is U torsion. Okay, now the argument that I gave last time for this to be torsion actually worked for only a compact manifold, because if M is not compact, then the equivariant homology may not be finitely generated. So this may not be a finite dimensional vector space. But it's always U torsion. Okay, so so if M is not compact, well, let's say M over M. Well, now we're looking at M over G. So if it's not compact, so it could look like this. With infinitely many holes, and then the cohomology would be infinite dimensional. Yeah. So then the cohomology would be infinite dimensional. But it's still, it's going to be zero above its dimension. Okay, but it's still zero above the dimension of M over G. So it's still U torsion. Okay. So that's for a free action. Okay. Now, I want to generalize this theorem to actions that's not free. Okay? And now, what is the definition of a free action? An action is free if the stabilizer of every point is the identity. Okay? So one way to generalize a free action, but not to make it too general, is to say that the stabilizer of every point is discrete. Okay? So that's called a locally free action. And it turns out that this theorem is true for a locally free action also. Okay? And now, in order to prove that, we need a few results from homological algebra or commutative algebra, about localization. And these results are not so difficult. So I think, it's good to prove them, So there are basically three results. So the first is that localization preserves exactness. So if you have an exact sequence and you localize, that just means that you invert U. Okay? Then the resulting sequence is still exact. So localization preserves exactness. And the second result is that localization commutes with quotient. So, if you have a submodule of a module over the polynomial ring, you can localize and then take the quotient, or you can take the quotient first and then localize, and the results are the same. Okay? So localization commutes with quotient. And the third result is that localization commutes with cohomology. So if you have a differential complex of R of U modules, and you take its cohomology and then you localize, you get the same thing as if you had localized the differential complex first and then take its cohomology. Okay? So I'm going to prove these three results. They are algebraic results, but but they may not be so readily available because, if you look at Attia's book on commutative algebra, he does localization for a more general, in a more general setting. We are just localizing with respect to U. Okay, so that makes everything a little bit simpler. Yeah. So let's look at localization theorems in algebra. So theorem 1 is that localization preserves exactness. Okay? And what that means is that if you have a sequence that's exact at B, so let's be more specific, is an exact sequence of R of U modules at B, then when you localize, it's still exact. So let's call these two maps F and G, and this F, U, G, U. Localization with respect to U is a functor, right? So recall that. Now, how is F of U defined? So if, so F of U applied to an element of AU. An element of AU is a fraction with a power of U in the denominator. And this is defined to be just F of A over U to the N. This is how you define this. Actually, these are equivalence classes, right? But I usually don't bother to write the equivalence class. That's how it's defined. And so if you start with the identity and you localize, then you just get the identity. You get the identity on AU. And then if you have a composition of two maps and you localize, then it's the same as GU composed with FU. Okay? So that just follows from the definition. So localization is a functor. Now, so let me see. First, I want to prove that localization preserves exactness. So let's prove this. Prove of theorem 1. Okay. Now, exactness at B means that the image of F is equal to the kernel of G. So there are two parts. The first part is that the image of F is contained in the kernel of G. So let's see. And so we want to prove the two parts for the localized sequence. And so we look at GU composed with FU. Okay. Now GU composed with FU is G composed with F, and then localize at U. And G composed with F is 0 because the original sequence is exact. Okay. So 0 localized at U, that's 0. And so this proves that the image of FU is contained in the kernel of GU. And now we need to prove the other direction. Okay, so the other direction is this. Okay, so let's start with something in the kernel of GU. So suppose GU of an element of BU, so B over U to the M, is 0. To be 0 means that it's equivalent to 0 over 1. Okay? So that's what we suppose. Okay. Then, that means there exists a K in the natural numbers such that U to the K times now what this means is that G of B over i.e. G of B over U of M is equivalent to 0, 1. Okay? And what that means is that when you cross multiply, it's torsion. So there exists a K so that U to the K times G of B minus 0 is 0, right? That's what this means. And but G is a morphism of R of U modules. So it's a morphism of R of U modules. That means you can bring the U inside G. Okay? So G of so U to the K times G of B is G of U to the KB. And so that's 0. Therefore, U to the KB is in the kernel. It is in the image of F. Okay? By the exactness of the original sequence, U to the KB is is equal to f of a for some a. And then, so B is equal to f of a over u to the k. And that's the definition of okay, now let's just leave it at that. And then our original element was b over u to the m. So b over u to the m is f of a over u to the k plus m. Okay? And that is equal to f u of a over u to the k plus m. Okay? So this proves that if you start with something in the kernel of GU, then it's in the image of f of u. So this proves that the kernel of GU is in the image of FU. Okay? Yeah, so that proves exactness of the localized sequence at BU. Okay? So therefore, AU to BU to CU is exact at BU. Okay, so this proves that localization preserves exactness. Yeah. And then, of course, you can extend it to a longer exact sequence. You just, because you have proved it one term. Okay, so at the other terms, it's the same. All right, so now that's the first theorem. Localization preserves exactness. Now, I mentioned that there are three theorems about localization. Okay, let's see how good your memory is. So what's the second theorem about localization? The first one is localization preserves exactness. Yeah, the second one is localization commutes with quotient. So if A is an R of U submodule of B, then you can take the quotient and localize. And that's isomorphic to first localizing the two modules and then taking the quotient. Okay? Okay. So let's see, how do we prove this? Well, when you have a quotient, then you have an exact sequence. So A is a submodule of B. Right, and then it projects to the quotient module. Yeah, so you have a short exact sequence. Just from the definition. But because we know that localization preserves exactness, That means you can localize and it's still exact. Okay? Yeah. Now, if this sequence is exact, then that says that this is the quotient of BU by AU. That's what, right? Yeah. So this says, yeah, because this map is surjective and its kernel is AU. Okay, so that's like, yeah, that theorem has a name, right? Like, that a module over the kernel is isomorphic to the image. Yeah. What do you call that theorem? Huh? It's one of the isomorphism theorems. Except I don't remember if it's the first, second, or the third isomorphism theorem. So this, yeah, so there's a map G here, right? So this implies that BU over the kernel of G is isomorphic to the image of G. And so BU over the kernel of G is AU is isomorphic to the image of G is B over A U. Okay? Yeah. Okay, so that proves that localization commutes with quotient. Yeah. And now what's the third theorem about localization? Yeah, localization commutes with cohomology. Okay, so if C is a differential complex, that means you have C0, C1, C2, and so on with a differential such that D composed with D is 0, then you can localize to get a sequence CU, which is C0. So in CU, that's C0U, C1U, C2U, where you localize the map DU, then this is again a differential complex. Okay, because DU composed with DU is D composed with D localized at U, and that's 0. Okay? So you can take the cohomology of these two differential complexes And the cohomology of the localized complex with respect to du is isomorphic to the cohomology of the original complex with respect to d, and then you localize at u. Okay? Okay, so, now it's basically just definitions and the previous two theorems. Okay. So the cohomology of Cu du, okay, by definition, okay, the cohomology in any degree, right, it's the kernel of du over the image of du. Well, let's do it for a specific degree. So the case cohomology is the kernel of du from CKu to CK plus 1u over the image of du from CK minus 1u to CKu, right? And now let's look at the kernel and the image, as part of an exact sequence. So the kernel of du, that's in CKu, and that goes into CK plus 1u. Okay? So the kernel fits into this exact sequence. It's exact here. So this is exact. No, just a minute. What do I want to say? I want to say, yeah, okay. The kernel of du fits into this exact sequence. Right. This is exact. Yeah, it's exact. That means it's exact here and exact here, right? And then another exact sequence. The kernel of d is exact. Okay. But localization preserves exactness, so since localization preserves exactness, I can localize this second sequence and I get an exact sequence. Okay? So I get this exact sequence. Yeah, but to say that this sequence is exact is precisely to say that this is the kernel of the U. So the kernel of D localized is equal to the kernel of DU. Okay? Yeah. So that says that localization commutes with the kernel. Mm-hmm. You can take the kernel and localize, or you can localize and take the kernel. Okay? I think, in fact, I don't need to say this first sentence, right? Yeah. Right. I start with this, I localize, then I know that the kernel of D localized is the kernel of D. Mm-hmm. Okay, now let's try to do the same with the image. Mm-hmm. Yeah, so I have to fit the image into an exact sequence. I have CK minus 1 going into CK. Yeah, so how do I fit the image into an exact sequence? Well, the image of this, if you want the image to be in an exact sequence, it has to be the kernel or something. So the image is going to be the kernel of CK over the image. Right. And this is a quotient map, so it's surjective. So we have this exact sequence. The image fits into an exact sequence like this. And then we localize. So you get CK minus 1U, DU, CKU, CK over the image of DU. Okay? And again, because localization preserves exactness, after you localize, it's exact. Okay? Yeah, however, yeah, now, yeah, this says that, well, this guy is the co-kernel of this map, right? So, yeah, so let's see. CKU over, let me give this map a name, pi, for projection. So CKU over the kernel of pi, right, is isomorphic to the image of pi. The image of pi is CK over image of D localized. But the kernel of pi is the image of DU. So this is CKU over the image of DU. Okay? Right. Okay, very good. And then you see, because localization commutes with quotient, this is CKU over the image of D, U. Okay? Localization commutes with quotient. Okay. So that's by theorem 2. This is by theorem 1. Localization preserves exactness. And now if you compare these two, well, then you see that image of DU is the image of D is isomorphic to the image of DU. Okay? Because these two, they are both the kernel of the projection map of this CUK. Yeah. Okay. So localization also commutes with the image. It commutes with the kernel and it commutes with the image. And now finally you go back here. Yeah. So the cohomology HK of CU is the kernel of du over the image of du, and that's the kernel of D. Localize it U over the image of D. Localize it U, and that's the kernel over the image. Localize it U, and that's the cohomology of C. Localize it U. Yeah, so that proves that localization commutes with cohomology. Okay. Yeah. So anyway, yeah, I think the proofs work out to be fairly straightforward. You know, if you try to prove theorem 3 directly, you find that it's quite difficult. But if you first do the other two theorems, then it's very easy. Okay. And now we want to apply this to a locally free action and prove the same theorem. And then next time we'll use that to prove the Borel localization theorem, with which we can finally compute the product structure of the equivariant cohomology of rotating a sphere. Because so far we still don't know the product structure. Right? So locally free action. I think I'll just make a definition and then we'll look at an example. So an action of a topological group. You need a topological group because you want to talk about the discrete topology, right? The action of topological group on a topological space X is locally free if the stabilizer of any point X is discrete for X in X. For any X in X. And so let's look at an example. Like S1 acts on C2 by lambda times Z1, Z2 is, say, lambda Z1, and then lambda to some power n Z2. Okay. So I guess I should fix a positive integer first. Let m be a positive integer. Then you have this action. Now what's the stabilizer of the origin? The stabilizer of 0, 0. What's the stabilizer of 0, 0? Huh? S1, right? Like, yeah, everything stabilizes. Everything, every lambda sends 0, 0 to 0, 0. So the stabilizer of 0, 0 is S1. That means 0, 0 is a fixed point. Okay? Now, what if the first coordinate is 0, but the second coordinate, no, sorry, here Z1, Z2, right? So the second coordinate is not 0. Yeah, so you need lambda n Z2 to be equal to Z2, okay? And so lambda to the n has to be 1. So this is nth root of unity. Okay. And then the stabilizer of Z1, Z2, when Z1 is not 0, that's the rest. What is that? So Z1 is not 0. So Z1 has to be equal to lambda Z1. That means lambda is equal to 1. Okay? Yeah. Okay, so now this group, this action is not locally free, right? Because this is not discrete. But if you remove the origin, then the stabilizer of every point is discrete. So the action of S1 on C2 minus the origin is locally free. Okay? Because these are discrete. But it's not free because if n is greater than 2, then it's not free, right? Greater than or equal to 2, and not free if n is greater than or equal to 2. Okay? Okay, so that's just an example of something that's locally free but not free. Okay, I'm going to stop here today, and then we'll continue next Monday. Okay? Yeah. And I already graded your homework, but I haven't recorded it. So anyway, I'll return your homework next Monday. Okay? And you have a problem set due next Monday also. All right, good. So I'll see you next week. Yeah.